Welcome to my new video, and now I'm going to show you what is inductance. So that's you all learned in fundamentals of electrical engineering what are inductors. Those are some non-resistive materials that act differently when there is some kind of alternating current in passing through them. For example, I think you'll know that some inductors store magnetic energy and some capacitors store electrical energy, and they act differently because when you pass some kind of voltage through them, they can change the shape of the equivalent electric circuit and so on and so on. But inductance in a coil is a very useful thing to know, because when you learn about electric machines, you can calculate what amount of energy goes to magnetize some magnetic circuits and to magnetize some motors and generators. So, and you learn the fundamentals of electrical engineering what is the impedance of a coil of an inductor. So it is very useful to know the terminology inductance of some coils. Okay, now here, if we have a magnetic circuit, we did some kind of examples and theory about this. Now we have a coil, we have a cross-sectional area of the magnetic circuit, the mean length of the core, and we pass a current. You know that there is going to be magnetic flux produced in the magnetic circuit, which is equal to flux. Which in this particular example it goes in this direction. But the flux linkage, this terminology flux linkage, is the amount of flux that is captured in this coil, and that is equal to the number of turns of this coil multiplied by the flux of the magnetic circuit. So flux linkage and magnetic flux is basically the same thing, but flux linkage is directed to this particular coil, sorry, and unit is, I forgot to say, Weber turn. So this small letter T is turn. Now, that inductance is measured by the flux linkage of the inductance of this coil is measured by flux linkage divided by electric current that is going through this coil. So, and the unit is Henry. This capital letter H is called Henry. Now, there's a lot of other ways that you can measure, or there are other ways that you can define what is the inductance of this coil. So, for example, if we put if we replace this with the flux linkage, this is lambda, Greek letter lambda, then we get that the inductance of this coil is the number of turns multiplied by the flux that passes through that coil and divided by the current passing through that coil. So, you know, for example, the flux is equal to the magnetic flux density multiplied by the area of the magnetic circuit. So we can say that the inductance is also equal to number of turns times the magnetic flux density times the area of the magnetic core, also divided by I. Now you know that the magnetic flux density is equal to the permeability times the magnetic field intensity in the magnetic circuit. Now you get something like this. This is also another way you can measure the inductance of the coil. Now, we know that MMF and I, this is the MMF magnetomotive force, which we discussed earlier in this course, is equal to H times L. No need to know what are the integrals and the derivatives of all of this. So that the I is equal to the magnetic field intensity times the length of the core and divided by the number of turns of the coil. So we can, for I, the current, electric current, say that is equal to HL divided by number of turns. Now, this is a double fraction, so this H and this H cancel each other out. This N, because it's in the denominator of the denominator, it goes to the numerator of the full fraction, and you get, and if we put, so H and H cancel each out, we can put N here and you get N squared, but we can put mu times A in the denominator of the denominator. So we get N squared is equal to the length divided by the permeability times the area of the magnetic circuit. Now this here, you remember that the reluctance of the magnetic circuit, is equal to the length divided by the permeability of the magnetic circuit times the area, cross-sectional area of this magnetic circuit. Now you get that the inductance is equal to the number of turns in the coil squared. So when you get, if you put many turns, you'll get bigger inductance. If you have a smaller reluctance of the magnetic circuit, you will get the bigger inductance. So when you, as a electrical engineer, and if you are going to design some magnetic circuits, magnetic motors and all of that, you want to make this thing a lot bigger. So the bigger of the inductance, the bigger you will get the magnetic energy in the magnetic circuit. So you always have to watch out with these formulas. There are pros and cons with this thing, because you can make a number of turns, I don't know, theoretically to infinity, but you know that the more turns, the longer the conductors of this magnetic circuit, so the resistance, electric resistance of this coil is going to be higher. So, and you have to put active energy to magnetize, more active energy to magnetize the magnetic circuit. But that's not now important. In these lectures you will see that in transformers, synchronous machines, DC machines, induction machines, and you will see how this is important. So these are the formulas. If you, for me particularly, this is one of the most important formula. And as you can see, reluctance varies and number of turns also varies. So L isn't the inductance isn't a constant. It can vary a lot because the BH characteristic, the magnetization curve, is not linear when you have some real magnetic materials. There are saturations, there are hysteresis, and you have some limits to this. But usually when you have our reluctance, this kind of stays the same. You will see that when I am going to do MATLAB examples, but it's gonna be not now, in some near future. I'm gonna do MATLAB, and you will see the graphics, how this changes when reluctance changes, when the permeability of the material changes. Okay, so now it was the introduction of this video was introduction to inductance, and in my next video, in my next two videos, we're gonna do examples of inductance, which is a very useful thing to know. And one more thing to say: there are not many ways. There are no devices that can measure this inductance. So usually you have to measure the inductance, which is never exactly correct, by these formulas you have here. So it's kind of a tricky part to measure the inductance. So you don't have many devices, many ways you can directly measure the inductance. So when you are an electrical engineer, you will have to do this in MATLAB mathematically, and yeah, that's one note you should know. So thanks for watching, and see you in my next video.